My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 463. In this lecture, we will try to understand VC dimension. How powerful is a class of models? Is there some way to measure the power or potential of class of models? When I say class of models, what I mean here is things like linear models. Can we somehow quantify or can we somehow give a number to this idea of how powerful our linear models? Similarly, can how powerful our linear models, isn't it? Similarly, can you say how powerful RBF SVMs? Can we measure how powerful our boosting algorithms? Is there some way, is there some numerical value that we can give to each of these models which can somehow capture this idea of how powerful a model is? Similarly, neural networks. Is there some way to do it? This is an important and interesting concept in the theoretical machine learning. So, there is an area of machine learning called statistical machine learning. There is also related areas like computational learning theory. This is the theory part of machine learning which says how powerful models are. It tries to prove bounds on how powerful models are. In practice, when you actually solve real world problems, do you notice that linear models are powerful than RBF SVMs, and you see that boosting is more powerful than others? So there is a practical way. You can take a bunch of challenging data set and you can show one class of models perform better than other models. This is the more practical hands-on way of doing it. The second way comes for your statistical machine learning or theoretical machine learning or computational learning theory, where we try to give numerical value to how powerful the class of models. This whole idea becomes extremely popular. One theoretical way to measure this is called VC dimension. VC here stands for Vapnik Chervonenkis. For those of you who may be confused, Vapnik is the same guy who involved SVMs. He's a brilliant Russian mathematician who came up with idea of support vector missions. There is a brilliant book by Vapnik himself. I think it's written by both Vapnik and Chernovonenkis. They are considered as father of statistical machine learning in some way, where they used lot of advanced statistics and advanced mathematics to come up with a concept called VC dimension. This is a very popular concept in the late 90s, when people were trying to come up with the mathematical reasoning, solid mathematical theory behind all of machine learning, and this was extremely popular in 90s. Even today it's very popular in theoretical part of machine learning, where researchers are trying to prove which model is better, which type of models are better than which other types of models, etc. From practical standpoint, from applied standpoint, we don't use VC dimensions as much. Let's be honest here, but you are a research student. If you want to understand, if you want to prove bonds, if you want to prove bonds, if you want to prove rigorous mathematics on each of these models, certainly VC dimensions is very powerful idea. It is used in research community, especially in statistical machine learning and in computational learning theory, but it is not used a lot in applied aspects of machine learning, not as much. Why we need VC dimension? Because we want to give a numeric value such that more powerful models has a larger value. Let's understand one way to do it. So the VC dimension itself, I will try to explain that with an example. Let's take linear models. What is the linear model? A linear model is a linear model is something where you have line, plane, hyperplane to separate your points, isn't it? If you have a line or plane or hyperplane as your decision surface, if you line or plane or hyperplane is your decision surface, such models are called linear models. Example, logistic regression. Our logistic regression is a linear model. Similarly, your linear SVM, not a kernelized SVM, that you must remember. Linear SVM, not kernelized SVM. Simple linear SVM is also a linear model because you are trying to find a linear plane that separates two classes of data, or your decision surface is a line or a plane. Let's see what is VC dimension means. Imagine I have only 2 points. I will try to explain with an example. Imagine I have 2 points. One is positive point and one is a negative point. Just see, one is, let me assume I have 2 points like this. This is my first point, this is my second point. I have 2 positive points. I may have points, 2 positive points like this, positive point, negative point. I may have positive point, negative points, isn't it? Let's assume I have only 2 points. So in whichever way these 2 points are organized, they could be like, not only like this could be like this. This is second way, this is third way. They could be in any way, isn't it? This is one possibility, this is another possibility, this is another possibility, isn't it? In any form, whichever way they are, I can always find a line to separate my positive points from negative points. Just see, I can always find, just see, I can always find a line to separate these points, isn't it? What it says, I can always find a line to separate my positive points from negative points, whichever way these are. Given 2 points, I can always find a way to split these points, to shatter these points. The keyword here is shattered. In VC dimension theory, there is also area called VC theory, isn't it? VC theory, where all this theory is built. Well, there is a bulky book written by Vapnik and Chervon and Keys discussing whole theory. This is called shattering. So given any 2 points, for example, these 2 points can be negative points also. Just see here, these 2 points here, if you have 2 points can be negative points also, like this. In such case you can write plain like this. These points there may be different ways. This is one possible way, this is another possible way, this is another possible way, this is another possible way, isn't it? Shorted, separated, isn't it? So given any 2 points, for example, these 2 points can be negative points. Just see, these 2 points can be negative points. I don't have any positive points. If I don't have any positive points, you can still shatter them. You can still shatter them, isn't it? In whichever way these 2 points are there in my space, then they could be like this. They could be like this also. This is 1 point, this is 1 point. Even I can shatter them. I can separate them. Shatter basically means that I am able to find. Shorter means what? I am able to find linear. I am able to find linear decision. Linear decision surface. Linear decision surface like a line, like a line in this case, because this is 2D, isn't it? In 2D, what is the linear decision surface? It's a line. Whichever way the positive and negative points are organized, as long as I have 2 points, I can always find linear decision surface that can shorter or that can separate my positive and negative points perfectly. So for 2 points, I can always find a line to separate. Let's check 3 points case. Let me check. This is about 2 points. Let me check 3 points. Let's see if I have 3 points, what happens. Let's assume I have 2 positive points and 1 negative point. Just see this one. I have 2 positive points and 1 negative point. In this case, how do I separate them? I can always draw a line to separate them, isn't it? Can I draw a line like this? Just see, I can always draw a line to separate them, isn't it? So, in whichever way my 3 points are placed, I can always find a plane or line to separate them. Just see, if I have 3 points, 2 positive points here, 1 negative point, I can always separate them. 2 negative points here, 1 positive. Means I am able to separate positive points and negative points. I can always find a plane or line to separate them. But question here is, what happens when you have 4 points? 3 points, we are able to shorter. We are able to shorter 2 points. What about 4 points? What if I have 4 points, isn't it? What if I have 4 points? Can I shorter 4 points? For example, if my 4 points are like this, for example, if my 4 points are like this, I can shorter them with this line, isn't it? I can obviously shorter them. If my 4 points are, let's say like this, I still can shorter them, isn't it? Like this. I can also shorter these positive points and the negative points, isn't it? Yes. What if my points are like this? What if my points are like this? Isn't it? This is 2D again. This is a very, very important case. If my 4 points are like this, can I draw a line which can separate them? Let's try. If I draw a line, just see, if I draw a line like this, what happens? I'm trying possibilities. If I draw a line like this, what's happening? Your positive point and negative point is this side. Again, negative point, positive point this side. Means I'm not able to separate positive points and negative points. Even if I draw a line like this, what happens? Here I have positive points, but here I have negative points as well as positive points, isn't it? I'm not able to do it, isn't it? Even if I write something like this, yes, here I have positive negative points, here negative points, isn't it? If I have positive points on both these sides, I can't shorter them. If I means I cannot shorter these 4 points, isn't it? Yes, whatever I do, I'm not able to shorter when I have 4 points like this. Here when I have 4 points like this, here I have 4 points like this, here I have 4 points like this, I can shorter. This I can shorter, isn't it? I'm able to shorter, but there exists one configuration. I'm able to shorter in this case, but in this case it is not possible. It's not possible. Not possible, isn't it? But there exists one configuration, at least one configuration of 4 points such that these 4 points cannot be shorted. This is important. There exist, I can say like this, there exist at least one configuration, there exist at least one configuration like this, which you cannot shatter using the linear model. Very interesting. Here, hence, the VC dimension of linear model is said to be 3, because this is the maximum number of points that can be shattered by linear model, which means given 2 points or 3 points, whichever way they are, whichever configuration they are, I am still able to shatter using a linear model, isn't it? With the 4 points, the moment I go to the 4 points, there exists at least one configuration where I am not able to shatter. So which is the maximum number of points that I can shatter by linear models for all configurations, for all possible configurations. So the given 3 points, I can always shatter them. Given 3 points, I can always shatter them. Of course, there is a theoretical proof for this. Here what I am showing to you is through an example. There is a very theoretical proof which shows that 4 points cannot be shattered by a linear model, and hence VC dimension of linear model is said to be 3. Just try to go through all these points. I will continue my discussion on VC dimension in my next lecture also, that is in lecture number 464. Thank you very much.